never goes away. It's always there no matter what functions you ever deal with. Product rule, quotient rule, chain rule are always going to be in play. Okay, let's do another one. How about this? Y is equal to e to the tangent inverse of x. Find the derivative of that. Well, this goes back to last class, doesn't it? Last class. We learned last class that the derivative of e to the x is itself, right? So we learned last class, derivative of e to the x is itself. So if I'm taking derivative of e to my hand, the derivative should be e to my hand, right? And then the chain rule says then I have to multiply it times the derivative of my hand. Yeah? So here we have the derivative of e to my hand will be e to my hand. So I'm just going to rewrite that, right? I'm just going to rewrite exactly what I see. It's itself. But times now what comes here? The derivative of the actual inverse tangent, which we just proved was 1 over 1 plus x squared. By the way, I'll mention on the bottom here, you can flip the order, make that x squared plus 1. Sometimes in some books they do it that way, right? Because it's addition, it doesn't matter. Okay? And there's really not much I could do here other than maybe put that on top of this, right? Because this is like underneath, so you could write okay, there. How about this one? How about secant inverse of natural log x? What do you see there? Composition, right? Composition. This is chain rule. You got a function inside of another function. So we start with the outer one. Yeah, so what's the derivative of secant inverse of something? Shoot, I don't know. We got to look it up, right? There it is. Right? The derivative of secant inverse of x is 1 over x times the square root of x squared minus 1. I'll just jot it down over here so I can use it. The derivative of secant inverse of x is 1 over x times square root of x squared minus 1. Okay? All right, so I don't have secant inverse of x, right? I have secant inverse of natural log of x. So I need to use that formula right here. But everywhere I see x, I'm actually going to replace it with what? Natural log of x. Good. So we've got 1 over, not x, natural log x, times the square root of the natural log of x, that squared, minus 1. That's weird, right? That just looks weird. But it's this formula with your x's replaced with natural logs. You'll see it? But I'm not done. Right? I've only taken the derivative of the outer layer of the chain rule. So I now need to go inside, take derivative of natural log. What's derivative of natural log of x? 1 over x. That's it. That's from last class again, right? You doing all right with this? Okay. I think that's, I mean, there's really nothing else to do. I mean, now you just have to practice, right? You have to do some problems. Problems in the section will be a mixture of, you know, some product rule, quotient rule, chain rule. It'll bring up functions from the past, you know. You might be dealing with trig functions or logs or exponentials. Do y'all feel like y'all need to see any more, or you feel like you have enough to get going? What do y'all think? Overwhelming response. Yes?
Can we do something with logs?
You want some, another, yeah, we can do something else with log. Let me throw a log in here that's not the natural log. Log with a different base.
Yeah,
Okay. Yeah, we can do that. Okay, so how about this? I'm going to give you log base 4 of sine x plus inverse sine x. For those of you who are taking Cal 2, there's something really, in Cal 1, you get the product rule, quotient rule, chain rule, right? And you learn all these derivatives of all these different functions. And then you get to a point where we're pretty close to being at this point where really, if anybody were to hand us a function, just like take the pot of all functions, right? Just have this big pot that has all the functions in it. If you were to just like reach in there and grab a function, the chances that we can find the derivative are pretty good because we know how to do all the rules. In Cal 2, if you take all the functions in there and you reach in there and grab one out and then try and do what's called the antiderivative, which is what Cal 2 is about, the chances you can do the antiderivative are almost essentially like zero. Antiderivatives are so much harder than derivatives because what you're doing in Cal 2 is you're taking our final answer and you're trying to figure out where it came from. Like that's the derivative of what? That's what we're doing in Cal 2. We're saying, that's a derivative of something, go tell me what that something was. And that's much harder to do because it's hard to see the chain rule and product rule and quotient rule in reverse. And there's no formulas for it. It's not like, oh, we have a product rule backwards or a quotient rule backwards. We don't have it in Cal 2. So the moral of my little story is that in order to do well in Cal 2, you must be proficient in Cal 1 derivatives. If you can't differentiate, if chain rule is just this thing, well, I got through Cal 1, but I never understood chain rule, Cal 2 will be an absolute nightmare for you because you can't go backwards if you never learned how to go forward. Does that make sense? So I see students who just like scrape by Cal 1 with a C. Somehow they get through, and then they get to Cal 2, and they have to take it once, twice, 3 times, 4 times. Then they change their major. When all they had to do was go back to Cal 1 and come out of there strong, and then Cal 2 would have been better, right? So really, I cannot emphasize enough how important it is for you to do your homework and practice, practice, and practice until you get to that point where it's not about, there's a famous quote that, I don't know who it's from. I used to put it on my website. It's no longer there on Canvas, but it says, don't practice till you get it right, practice until you can't get it wrong. Those are completely different mentalities, right? Oh, I got it right, yay. No, you want to get to the point where it's like, give me a problem, I'm going to get it right, okay? I'm not going to get it wrong. That's a confidence in your ability, right? So as the whole reason I started thinking about that is with these problems, the thing that's good about them for me is I can make them up because pretty much we have all the tools to handle anything I put up on the board. Like it doesn't matter what I put up here, we should be able to follow the rules through it. Okay. Well, what do you see? Chain, right? Composition or chain, we can say it both ways. So we see an outer function, right? And then inside, what do you see? Not a product, right? It's a sum. So that's good because I can do those derivatives separately when it comes time, right? But we'll start with the outer first. So from last class, we had a formula or rule from last class that if you take the derivative of log with some base of x, base a of x, what's the derivative of that? 1 over x times natural log of A. So A is a number, right? A is the number that's down here as your base. So what you do is you do 1 over x and then multiply times natural log of whatever that number is. Okay? So here the base is 4, right? So my derivative will be, first of all, this is like the x. That's like the x in that formula. So it's going to be 1 over, right, big division here, everything in there, sine x plus inverse sine x, right? That's what this is here, right? That's 1 over whatever was inside the argument times natural log of 4. So I'm going to put times natural log of 4 here. Is that right, the way I have that written? What's wrong with that? I have to have parentheses around these two because whatever this is gets hit by that. And if you don't put a parentheses, the only thing that's getting hit by the natural log of 4 is that one, right? So you have to have parentheses here. Am I done? Nope. I need to multiply by the derivative of what's in here, but that's a sum, so I can do them separately. I will have two answers, so I'm going to put a parenthesis here. Derivative of sine of x is cosine x, and then plus, now derivative of inverse sine x, that's different, right? That's 1 over square root of 1 minus x squared. There you go. There's your derivative. It's not pretty, but it's the derivative, right? That helpful? What if I had given you this problem and I didn't put any number there like that? What if I'd given you that? The base is 10. So that would change. The only difference in the answer would be that's a 10, right? Okay. All right, so practice, okay? Do problems out of this section. And then next time, if you have any questions you want to talk about, we can.
And that's from section 3.5?
3.5. Yep. Let me check it real quick on the homework assignment, what it is for this. One through six, and you know what? Don't even worry about 1 through 6. 1 through 6 is a refresher on pre-cal, and what you'll probably do is get frustrated because it's been so long since you've done pre-cal. It's problems like this. Well, don't even worry about it. 16 through 27 are the derivatives. These are all problems where you practice taking derivatives, okay? All right, we're going to move on. All right, this is an important section, all right? Really, really, really important section. 3.7. Indeterminate forms and what? What's rule? How do you say that? Looks like La Hospital, right? Almost, or something. It's pronounced L'Hopital. L'Hopital's rule. Okay, L'Hopital's rule. So what we're about to do is going to seem weird. When we started this class, right, day one of this class, we started with the idea of the limit, right? We did limits, right? So we started with this idea of the limit. And then from that, we've branched out and we said there's a special limit there's a very special limit. It's this one. The limit h goes to 0, f of x plus h minus f of x all over h. And that is actually defined to be the derivative, right? The derivative is just a limit, right? It's just a limit. And then after we did that, we said, hey, guess what? That's really hard to do. We have a bunch of rules. Product rule, quotient rule, power rule, product rule, quotient rule, chain rule. We have ways of doing derivatives without having to do the limit each time, right? But we started the class with the idea of the limit. And you all remember it kind of sucked having to do all those limits. There was a lot of algebra, right? So what we're going to do in 3.7 is we're going to go back and do some more limits. And that might initially sound really bad, but L'Hopital's rule is going to be this like saving grace. It's going to be this thing that makes us really happy, all right? So here's what I'm going to do. I'm going to start by going back to a problem I gave you way back in the beginning of class. We're going to do the problem the way we did it at the beginning of class. Then I'm going to show you L'Hopital's rule, and we're going to use his rule to do the actual problem. Then you're going to be like, wow, that was easy, okay? So let's go back and let's do this example. Limit, let's go limit x approaches 2 of x squared minus 4 over x minus 2. You all remember how to do limits? It's been so long. What's the first step to do any limit problem? Just plug it in, right? We call that direct substitution. Just see if you can let the x turn into a 2 and see what you get. So replace all your x's with 2's, and what do you get? 0 over 0. And what did we say back in the beginning when we saw that? We said this was bad, right? We said bad, right? This is bad. And then we would need to do algebra or a trick, right? We need to do algebra or a trick. So we'd say this is bad. We need some algebra, or we need some sort of trick to do this. And what was the algebra for this one? Difference of squares on top, right? You'll see the difference of squares on top. So we would do a little algebra. The top would be limit x approaches 2. We rewrite the top as x plus 2x minus 2. And then we cancel x minus 2, right? And now take the limit again, and what do you get? 4, right? 2 plus 2 is 4, so we're done. That's the limit. That's the way we did it, right? That look familiar to everyone? That's a pretty easy problem, but we had to do some algebra, some sort of trick, right? Let me now show you. I'm going to do this same example. I'm going to use L'Hopital's rule, and I'm going to verbally tell you what the rule is. After I verbally tell you and we finish the problem, I will actually put the actual precise rule up on the board, okay? The actual formula for it. So let's do the same problem with L'Hopital. All right, so limit x approaches 2 of x squared minus 4 over x minus 2. First thing we do, direct substitution, we get 0 over 0. And before we would say at this point this is bad, we need to do some algebra or some trick, right? We are now going to say, yes, this is bad. Algebra and trick are an option, but we also have this thing called L'Hopital's rule. All right? Here's what the rule says. If you ever get 0 over 0, okay, if you ever see 0 over 0 in a limit, then instead of doing the algebra or some trick, here's what you're allowed to do. Take the derivative of the top and take the derivative of the bottom separately, not quotient rule. Just take the derivative on top and bottom separately, and then try the limit again. It's weird, right? Let's do it though. I'm going to say equals limit x approaches 2. What is the derivative of the top? 2x, right? Just 2x. Yes? Over, what's the derivative of the bottom? 1. Okay, now try the limit again. What do you get if you replace the x with 2? You get 4, right? These answers are the same. That's not a coincidence. That's what L'Hopital's rule lets you do. Wasn't that nice? Now, I need a way to let you know, someone who's looking at my work, I need to let them know that between here and here I used L'Hopital's rule. So the standard technique for this is right above this equal sign to either write capital H, that's what a lot of textbooks do, or you can do an H with a circle around it, or you can do a capital L, or you can do a capital L with a circle around it. Something to let people know you use L'Hopital's rule. I am going to use an L with a circle around it to let you know that I've used L'Hopital's rule. What you don't want to do is say that this equals this without telling anyone that you did use a rule, right? Because then it's not, I mean, you did weird stuff here that isn't allowed. You can't just change this expression, right? You used the rule. Is that okay? Man, that's nice, isn't it? Let's do a couple more examples before I actually formally give you the rule, all right? Let's try this one. How about this? Limit x goes to infinity of 3x squared plus 1 over x squared minus 3. X is going to infinity. So what happens if I try and, well, I can't plug infinity in, but I can think about a number that gets really big. What happens on top here? Big number squared times 3 plus 1. Where's the top headed? Positive infinity, right? So the top's headed to infinity. Where's the bottom headed to? Infinity squared, take away 3. It's still huge, right? So the bottom's headed to infinity. We have infinity over infinity. In the past, when we saw infinity over infinity, that was bad, right? That's an indeterminate form. We don't know what's happening. So we had to do some sort of algebra, some sort of trick, right? Where's that formula sheet? There it is. Remember this? This thing right here? If we had 0 over 0, algebra trick. Infinity over infinity, algebra trick. Remember all these? Ooh, these sucked, right? These all sucked. And we'll get to it, all right? Just hang tight. Oh, I was going to say something. I didn't say what I wanted to say. All of these right here, when you take a limit and you get things like this, these are all called indeterminate forms. That's when the title of this section is Indeterminate Forms in L'Hopital's Rule. It's saying, hey, when we get any of those forms that we saw on that table, any of those indeterminate forms, right, we can try and use L'Hopital's rule. Okay, does anyone remember how to do this problem, like before L'Hopital? I'll remind you, and you won't be happy. This is that one where we would have to come out here and we'd say, oh, what's the highest power of x here? Let's kill that off. I put a 1 over x squared out here, and then out here a 1 over x squared. Remember that? Yeah? And then like distribute that through and distribute that through. Does that look familiar? Yeah? Well, not anymore. We don't need to do that anymore, okay? Here's what we do instead. I'm going to not do that. And instead, I'm going to use L'Hopital's rule. And I'm going to take the limit as x goes to infinity. I'm going to take the derivative of the top and bottom separately. So what's the derivative of the top here? 6x. What's the derivative of the bottom? 2x. Okay, at this point right here, you can cancel the x's. Right? And you're left with 6 over 2, which is 3. Your answer is 3. Man, wasn't that nice? Isn't that great? Let's do another. See if you remember this one. Y'all loved these. I got all these emails. People were calling me on the weekends asking me to give them more problems like this. put these on the test, that you loved them. Limit theta goes to 0 of tangent 5 theta over sine of 3 theta. Who remembers how to do this? We get 0 over 0 here, right? Tangent, if you try and plug in theta is 0, you get 0 on the top, right? 5 times 0, 0. Tangent of 0, 0. 3 times 0, 0. Sine of 0, 0. So you get 0 over 0 here, right? You all remember this is the one where we rewrote things and like pulled everything apart, and we said, oh, it'd be real nice if we could like have a 5 theta here, so let's make it appear. Let's do a 5 theta over 5 theta and slide this over, and then, remember all that? Okay, you loved it, right? So now instead we're going to use L'Hopital, because we get 0 over 0 here, right? This is 0 over 0. So I'm going to use L'Hopital. And L'Hopital says that I am allowed to just take the derivative of the top and bottom separately. All right, what's the derivative of the top? Be real careful here. Secant squared of 5 theta, a little bit more, chain rule, times what? 5, good. Remember, you have to go in here and take the derivative of 5 theta. You're treating theta like your variable. So this is like derivative of 5x would be 5. The derivative of 5 theta would be 5. Understand where the 5 comes from? Okay, over, now, what is the derivative of sine of 3 theta? Cosine 3 theta times what? Times 3. Great. Well, what now? We got to try and plug theta in, right? Theta is 0. 5 times 0, 0, right? Here I'm going to do secant of 0 and then square the answer. Hey, what's secant of 0? Well, that's the same as, secant is the same as 1 over cosine, isn't it? Secant of 0 is the same as 1 over cosine of 0. What's cosine of 0? 1. So this is just 1 over 1, which is 1. So this secant of 0 is 1, and then square that, you get 1. And 1 times 5 is 5. So you get 5 on top. And then here, that's a 0, right? 3 times 0. Cosine of 0 is 1 times 3. You get 3. So your answer is 5/3. Isn't that better than like ripping everything apart and trying to see what, make something appear? And who has a question on this? You're okay? Yes?
Could you like re-say the whole thing?
Yeah. Like from where?
After when you explained the secret.
Okay, so this right here, right? That right there, when I plug 0 in here for theta, this becomes 5 times 0, 0, right? So what I have circled here is secant of 0. I need to know what that is. Well, secant of 0 is 1 over cosine 0. You all right with that? And cosine of 0 is 1, right? So this is really 1. So 1 over 1 is 1. So everything I have circled here is 1. And then I'm squaring it. 1 squared is 1. And then times 5. So I get 5, right? And on the bottom, this is 0, right? 3 times 0. Because I'm taking the limit. So I'm saying, what happens if that turns into 0? 3 times 0 is 0. Cosine of 0, we said earlier, is just 1. So then you multiply times 3. Good. No, thank you for asking. Any others? Yes?
Based on the last one.
Yeah.
When you pass out,
Yes.
the last step, can you explain that one more time? Like, because I would think like if I'm sending it to infinity, they'd be like I got confused because I was writing at the same time when you're explaining it.
Okay, so when we were at this step, we had 6x over 2x when we took the derivative, right? So if we take the limit right now and let x go to infinity, the top goes to infinity, the bottom goes to infinity, right? But this is exactly x and that's exactly x, right? So let's say I take a really big number, right? Let's say I take like, I don't know, 1 million. You could argue if that's big or not, but let's just say I take 1 million. If x is 1 million, what would 1 million over 1 million be? 1, it would just go away, right? If it was 2 million over 2 million, it would go away. The fact that these are identically the same thing, x and x, I can cancel them out or reduce them. Now up here I can't do that because the top and bottom, they're both getting big, but they're not exactly the same, right? Like 3x squared plus 1 is not the same as x squared minus 3. So you can't cancel them because they're not identical. That's why I canceled them here. Is that okay? No, I didn't cross it out. I asked myself, what is cosine of 0? So cosine of 0 from pre-cal, when you're at the angle 0, you're here, right? That's your angle 0, and cosine is the x-coordinate there. That's the point 1, 0. Cosine is the x-coordinate, so it's 1. What do y'all think of this rule? Yeah? I'll show you one more example before we have, well, we're going to do more examples, but let me show you one more. Limit x goes to 0, sine x over x. First of all, what happens if you try direct substitution? You get 0 on top, right? Sine of 0 is 0. You get 0 on top, and 0 over 0 is 0 over 0, right? It's bad. Yeah? So you do some algebra, some trick here. If you go back in your notes and you take a look back when we got to this problem, I actually told you all what this answer was, and I told you I couldn't prove to you why it was that answer. This was that problem where we had, remember, sine of junk over junk? And as long as the junk matches and the junk goes to 0, your answer is 1. But I said just take that on faith. That's what I told you. Just believe me when I tell you that. But now I can actually prove to you why the answer is 1. But I have to use L'Hopital's rule to do it. So I do get 0 over 0, right? So I use L'Hopital. And I take derivative of the top, derivative of sine x is cosine x, over derivative of the bottom, which is 1. And now let x go to 0. What's cosine of 0? 1. 1 over 1 is 1, and your answer is 1. There we go. What a rule. What a rule. In my homework solution videos, you'll hear me, I have like a little it's not a song. Anytime I use L'Hopital in my video, you'll hear me, I'll be like, L'Hopital, because I'm always so happy to use L'Hopital. It's just such a great tool, right? So I always have students ask me, why did we torture ourselves with limits? Right? Why did we torture ourselves with limits? Why didn't I just give you L'Hopital's rule in the very beginning? What are your thoughts on that? I mean, it would have been nice to have this earlier, right? But why didn't I? Was it to literally torture you, or what? What? Okay, so maybe I wanted you to have to go through the limit suffering a little bit?